Imagine looking up at the night sky. For millennia, humanity has gazed upon the stars, believing them to be fixed points in an eternal, unchanging heavens. We saw constellations that told stories of gods and heroes, patterns that guided sailors across vast oceans. This cosmic canvas seemed steady, predictable, and fundamentally static. It was a comforting thought, suggesting a universe with a certain permanence, a reliable backdrop to our fleeting lives on this small blue planet. This ancient view of a serene and motionless cosmos was not just a romantic notion. It was the bedrock of our understanding of reality for a very, very long time. But what if that picture is wrong? What if the universe is not static at all? What if everything you see, from the closest star to the most distant galaxy, is actually rushing away from us? This is the reality that modern astronomy has revealed. The universe is not a quiet, still place. It is a dynamic, expanding entity. Every galaxy is moving away from every other galaxy. It is as if the entire fabric of space itself is being stretched, carrying the galaxies along with it for the ride. This discovery fundamentally shattered our classical view and introduced a new, more chaotic, but ultimately more exciting vision of the cosmos. This expansion is not just a curious footnote in a science textbook. It is the central drama of our universe's story. It tells us about its fiery birth in the Big Bang, some 13.8 billion years ago. It also holds clues about its ultimate fate. Will the expansion continue forever, leading to a cold, dark, and empty future? Or will it eventually slow down, reverse, and collapse back in on itself in a big crunch? The rate at which the universe is expanding is the key to answering these profound questions about our cosmic past, present, and future. It is one of the most fundamental numbers in all of cosmology. Understanding this expansion is therefore not just an academic exercise. It is a quest to understand our place in the grand scheme of things. By measuring how fast the universe is growing, we are essentially taking its pulse. This measurement, known as the Hubble constant, allows us to calculate the universe's age, its size, and the very laws that govern its evolution. Getting this number right is crucial. It underpins everything we think we know about the cosmos. But what if our measurements do not agree? What if the universe's pulse seems to be beating at two different speeds at once? To measure the expansion rate of the universe, astronomers have developed incredibly clever techniques. One method involves looking at the local universe around us. Scientists observe relatively nearby stars and galaxies. They use special types of exploding stars called Type Ia supernovae as standard candles. These cosmic lighthouses have a known brightness, so by measuring how faint they appear, we can calculate how far away they are. By also measuring how fast they are moving away from us, we can calculate the expansion rate right here, right now. This method gives us a direct look at the universe's current speed of growth. Another powerful method takes us back in time all the way to the universe's infancy. Scientists study the faint afterglow of the Big Bang, a sea of radiation that fills all of space, known as the cosmic microwave background, or CMB. This ancient light carries a detailed snapshot of the universe when it was just 380,000 years old. By analyzing the tiny temperature fluctuations in this light, cosmologists can build a precise model of the early universe. This model, which includes ingredients like dark matter and dark energy, predicts how the universe should have evolved and what its expansion rate ought to be today. Here is where the cosmic mystery begins. When we use the first method, looking at nearby supernovae, we get one number for the expansion rate. The data consistently suggests that for every megaparsec of distance, that's about 3.26 million light-years, the universe is expanding at about 73 kilometers per second. This is the value we measure when we observe the universe as it is today. It is a figure honed by years of painstaking observations from powerful instruments like the Hubble Space Telescope. It seems solid, reliable, and based on direct evidence from our cosmic neighborhood. But when we use the second method, based on the light from the baby universe, we get a different number. The model built from the cosmic microwave background predicts that the expansion rate today should be slower, around 67 kilometers per second per megaparsec. This isn't a small difference. It is a significant, persistent, and deeply puzzling disagreement. Both methods are incredibly precise, and the scientists behind them are among the best in the world. Yet they give us two different answers to one of the most fundamental questions in science. How fast is our universe expanding? This discrepancy might sound like a minor detail, a simple squabble over a few numbers after the decimal point. But in cosmology, this is a chasm. It is a profound conflict between two of our most successful ways of understanding the cosmos. On one hand, we have our measurements of the universe as it is now. On the other, we have our predictions based on our understanding of the universe as it was then. The fact that they do not align suggests that something is fundamentally wrong. It's like measuring a child's height today and finding it doesn't match the height you'd expect based on their growth chart from when they were a toddler. This problem has a name, the Hubble tension. It is one of the most pressing and exciting challenges in modern physics. The tension signals that our standard model of cosmology might be incomplete. It is a crack in the foundations of our cosmic understanding. It could be that there are subtle errors in our measurements that we have not yet found. Perhaps the supernovae we use as standard candles are not as standard as we thought. Or maybe we are misinterpreting the ancient light of the CMB. However, the more data we gather, the more the tension seems to persist. This raises a far more thrilling possibility, that the disagreement is not due to error, but is pointing towards new physics. Perhaps there is a mysterious new ingredient in the cosmic recipe that we haven't accounted for. Maybe there was an unknown type of particle or energy in the early universe. Or perhaps the nature of dark energy is more complex than we currently believe. The Hubble tension, therefore, is not just a problem, it is an opportunity. It is a clue, left by the universe itself, that there is more to discover. It forces us to question our most basic assumptions. Solving this puzzle could lead to a revolution in our understanding. It is a cosmic tug-of-war, with our understanding of the universe hanging in the balance. And as we venture deeper into this mystery, we are charting the unknown territory of reality itself. Scientists are not standing still. They are actively designing and deploying a new generation of powerful observatories both on the ground and in space, with the primary goal of shedding light on the Hubble tension. So where does this cosmic tug-of-war leave us? It leaves us in a state of thrilling uncertainty on the cusp of discovery. The Hubble tension is not a sign that cosmology is broken. It's a sign that it is vibrant and alive. It's the friction that sparks new ideas and illuminates the path forward. Whether the solution lies in a subtle error in our stellar measurements, or in a dramatic new piece of physics, the journey to find it will undoubtedly deepen our understanding of the universe. It's a reminder that the cosmos is not a static, solved puzzle, but an active, unfolding story with surprises still in store. The quest to understand the universe's expansion is, in many ways, a quest to understand our own origins and destiny. The rate of expansion tells us the age of our cosmos, the story of its evolution, and the likely scenario for its ultimate fate. It's a number that connects the fiery birth of the universe in the Big Bang to the vast star-filled expanse we see today, and onwards into the deep future. This journey into the unknown is a fundamentally human endeavor. It speaks to our innate curiosity, our desire to look up at the sky and not just see points of light, but to understand what they are and how they came to be. The Hubble tension is the latest chapter in a long story of cosmic exploration, from the ancient astronomers charting constellations to Edwin Hubble revealing a universe of countless galaxies. Every generation has faced its own set of puzzles, and every solved puzzle has revealed a universe far grander and more intricate than previously imagined. This mystery is our generation's call to explore. As we stand here today, on this small planet, looking out at the immense cosmos, we are armed with unprecedented tools and an unshakable curiosity. The Hubble tension might seem like a complex, abstract problem, but at its heart, it's about a simple, profound question. How fast is our home, the universe, growing? The fact that we do not yet have a single clear answer is not a cause for despair, but for excitement. It means there is more to learn, more to discover, and more wonder to be found in the magnificent, expanding universe we are privileged to inhabit. The search continues.